Hello and welcome to our next lesson for Extension 1. Today we're going to be looking at the binomial distribution. So last time we looked at the Bernoulli distribution. Now that's where we only had the two possible outcomes, or either a failure or a success, but it was only one trial, only one thing was occurring. We weren't doing multiple trials. What we're going to look at today is the binomial distribution, where we are repeating Bernoulli events. So basically what we're doing is we are having numerous trials, some set number n, where we're going to see how many times that particular failure or success will occur. So if we were to flip a coin 50 times, that's obviously going to be a binomial distribution because the probability for each one of those 50 trials is going to be the same. Right? This is that same thing as last time, is the failure and the success don't have to have the same probabilities, but the probability of success has to stay the same every single trial. So if we picked out, or we're looking at the number of red cards that we could pick out from a deck of cards without replacement, well, that's not going to be a binomial distribution because every time we pick out a card and we don't put it back, the probability is going to change for the next card that we draw. That probability of success or failure is going to change because we're going to start off with 52 cards, and then it's going to be out of 51 cards, 50 cards, and so on. Right? So it's important that they're identical Bernoulli events. Right? The probability has to stay the same every single trial. So a binomial random variable is then the number of successes that we get from n Bernoulli trials. Right? So it's however often we get a certain number of successes or failures. So let's look at an example. Finding the probability of each event, we can leave the answer in index form. So what's the probability of getting 10 tails when we flip a coin 10 times? So we know that the probability of getting a tail is going to be a half, and we know that the probability of not getting a tail is also going to be a half. So the probability of getting 10 tails in a row is going to be the probability of getting a tail multiplied by the probability of getting a tail, and so on, 10 times. And if we multiply a half by a half by a half by a half, well, that's just going to be 1 over 2 to the 10, because it's 2 times 2 times 2 times 2, 10 times. What's the probability of getting 8 red marbles when selecting 8 marbles at random from a bag that have 10 red and 11 blue marbles? So this doesn't say with or without replacement, but because we're looking at it being binomial, we're assuming that we are going to put them back. Because if we don't put them back, the probabilities are going to change. So assuming that we are doing replacement, we've got 10 ways that we can get red marbles out of our total of 21 marbles. So the probability of getting a red is just going to be 10 out of 21 for each trial, assuming that we are doing replacement. So therefore, the probability of getting 8 reds is going to be 10 over 21 times 10 over 21, 8 times. So if I multiply those together, what we're going to have is 10 times 10 times 10, 8 times on the top, 21 times 21 times 21, 8 times on the bottom. So it's going to be 10 to the power of 8 over 21 to the power of 8. All right, so our probabilities for both those examples staying the same. So here we have our old friend, Pascal's triangle. And not only, well, the last time we looked at it was to do with binomial expansion, all right, when we had x plus y to the power of 7, for example. Our coefficients came from Pascal's triangle. What we're going to use it for today is binomial distribution. So if I flip a coin twice, I can get the following outcomes. I can get 2 heads and no tails, one way that that'll happen. I can get 1 head and 1 tail, 2 ways that that'll occur, a head and a tail or a tail and a head. And then 2 tails, I can only get that one way. 2 tails, no head. If I flip a coin 3 times, well, I can get 3 heads one way. I can get 2 heads and 1 tail 3 ways. Head, head, tail, head, tail, head, or tail, head, head. Likewise, I can get 3 ways of getting 1 head and 2 tails, or there's one possible way that I can get 3 tails. That's starting to look like we can see a pattern. So then if I was going to flip a coin 4 times, what do we think our possible options are going to be? All right, keep in mind that every single time we're going, like if we look at the last time, it was 3 heads, 0 tails, and then 2 heads, 1 tail, 1 head, 2 tails, 3 tails, no heads. So we are going down as far as heads and tails, but our coefficients, or how many ways that we can get that, are coming straight from Pascal's triangle. So for flipping a coin 4 times, I can just go straight to the 4th row and say, well, there's going to be 1 way that I can get 4 heads. There's going to be 4 ways that I can get 3 heads and 1 tail. 6 ways that I can get 2 heads and 2 tails. 4 ways that I can get 1 head and 3 tails. And 1 way that I can just get 4 tails. So straight away, that multiplier out the front is just our coefficient straight out of the appropriate row from Pascal's triangle. And then we're just going, starting with however many times we've got for heads, that number decreases and our number of tails starts at 0 and increases. So then finding our probabilities, because hopefully we remember that Pascal's triangle, that was just our n choose r for each one of those specific values in Pascal's triangle. So when we have the probability P, which is for success of a particular outcome, then the probability of R successes occurring over n independent trials, keep in mind independent means that each individual trial does not affect the next trial, then the probability that our random variable equals R, the number of successes, well, that's going to be n choose R multiplied by PR or multiplied by 1 minus P n minus r. Remembering that 1 minus p is the same as saying q, the probability of not success. N is always going to be the number of trials that we're doing, and r is how many successes we are hoping to get. Now, sometimes you'll see that written as our random variable x for it's bin. Everyone says bin, but it's bin because it's short for binomial. So bin of np, where n again is our number of trials that we're doing, and p is our probability of success. All right, that's just shorthand. You may very well see that. That does usually pop up as a multiple choice question in the HSC. Example 2. All right, so Maria is going to flip 8 coins. Well, let's assume she's flipping that 1 coin 8 times. Find the probability that she gets exactly 5 heads. All right, so we want to find out how many times she is going to get the head come up 5 times. Note it says exactly 5. So we know what the probability of a head is going to be, and we know what the probability of not a head or a tail is going to be. Both of those are just a half, 0.5. All right. Probability of, what are we looking for? Heads. So probability of a head, 0.5. Q, probability of a tail or not a head is also 0.5. So now we're just going to substitute that into the formula from the previous slide. So we've got NCR, PR, Q, N minus R. This is for R successes. So N is the number of trials, so N is going to be 8. R is our how many that we want to get, so in this instance it's 5. P is our probability of success, which is 0.5. And Q is our probability of failure or tails, also 0.5. Now, you don't have to try and work out now what's 8 choose 5, draw up Pascal's triangle. You can type that exactly as it's written on the screen into your calculator. And your calculator should come back with 7/32. Now, obviously, it's going to come back with some sort of a decimal first. You just hit the S to D button, fraction to decimal, or whatever it's on your calculator it says, and that'll convert the decimal into 7/32. Right, so that's the probability that if she flips the coin 8 times, she gets heads come up exactly 5 times. Example 3. Right, we've got a hydrangea plant. It's got a probability of 1/3 that it's going to produce white flowers. If we've got 4 plants growing, find the probability that only one of those plants will produce white flowers. All right, so again, our probability of white is going to be 1/3. So therefore, the probability of not white is going to be 2/3. Now, we're going to say not white because there are numerous possible colors that it could be. We're not going to list them all. It's just either success or failure. It is going to be white or it's not going to be white. So again, we're just using our formula from before. NCR, PR, 1 minus P, N minus R. Now, whether you have 1 minus P or Q, it doesn't matter because it means the same thing. Right? We looked at that last week. So R successes, well, we want only 1 plant. So R is going to be 1. N is our number of trials. Well, in this instance, number of plants, so that's going to be 4. P is 1/3, 1 minus P, 2/3. All right, so again, we can just type that straight into the calculator exactly as written. Obviously, you don't need to the power of 1, but I've just written that in there because that is what our R is. And again, our calculator comes back with a decimal. We can convert it to a fraction because this is not a nice decimal, 32 over 81. All right, both example 2 and example 3, we're talking about only one plant, or exactly 5 times that it comes up heads. Right? We've got an exact number. Example 4 is now different. All right, so we've got a certain type of machine in a car assembly plant that has an average probability of 0.1 of breaking down. If the assembly plant has 8 of these machines, what is the probability to 3 decimal places that at least 6 will be in working order at any one time? All right, so note that this time we're talking about at least 6 machines are working. So if we're talking about at least 6, well, we're talking about the probability that 6 are working, or the probability that 7 are working, or the probability that all 8 are working. So we will have to consider that. First thing is we've got a probability of 0.1 of breaking down. So if breaking down is 0.1, that means the probability of working is going to be 0.9. All right, it's either it's working or it's not working, broken or not broken, depending on which way you want to look at it. We're talking about these machines working. What's the probability that at least 6 are working? So then our probability of success is 0.9 and our probability of failure is 0.1. Right? Don't go on the assumption that the only probability that you're going to be given is the probability of success. Right? This is an example where you're given the probability of failure. Will that trip you up and give you the wrong answer? Absolutely. You do need to be wary of that. So as I said before, the probability that we've got at least 6 working is going to be the probability of 6 plus the probability of 7 plus the probability of 8 machines working. So we need to put into our formula from before all the numbers that we've got. Remember that I was saying that 0.9 is our probability of success and 0.1 is our probability of failure. So then it's 0.9 to the power of 6 and 0.1 to the power of 2. Right, for probability of 6. Because if you switch those numbers around, you're going to get the wrong answer. All right, so again, probability of 6, probability of 7, and probability of 8, as you can see there. Again, I've written 0.1 to the power of 1 so that you can see it. And then in that last one there, we've got 0.1 to the power of 0, because that's what it would be. They're all working, so there are none that are failing. Again, you don't need to type that in your calculator. I've just got it in there for completeness. But regardless whether you drop that last bit off or if you put the whole thing in, you're going to get the same answer, and your calculator should come back with, it says to 3 decimal places, 0.962. It is important that you give the answer in the required format that the question specifies. Right? Once 3 decimal places, decimal places. If it's a long, horrible decimal, turn it into a fraction. It'll be rare that you'll have a long decimal that won't turn into a nice fraction. That should always give you a nice fraction. But that brings us to the end of this particular exercise. All right, so this is going to be chapter 1502, which is on page 678. I can't remember if there was anything off the top of my head with that particular chapter that I wanted you to skip or do anything weird with. So do give it a go. As always, let me know if you're having any problems or if I've made any more typos. I don't think I had any this time, but I didn't think I had any last time. Email or Google Classroom, send me a message either way, and I will get back to you. Hope you're doing well, and we might actually look into organizing a time where we can have like a Zoom chat or something. I'll be in touch with that one. Otherwise, have fun, and I will talk to you soon.